Most efforts in the area of legged locomotion have been aimed at complex active mechanical systems using as many as 7 degrees of freedom and requiring very large control systems. Consequently, the motions of these machines have been quite awkward and clumsy, and certainly do not mimic human walking. Human walking is essentially passive, requiring very little muscle interaction to achieve the motion of the walking. A robot based on this concept would require far less control and power, and would be inherently simpler and more efficient. Passive dynamic walking is simple. It is a simple interaction between gravity and inertia that sustains a steady walking cycle on a downhill slope. No motors or actuation are necessary to achieve this motion. Take, for example, a slinky. As you give it a push down the stairs, the slinky coils and uncoils, and the interaction between the spring and gravity allows it to walk down the stairs. Tad McGeer at Simon Fraser University used a similar concept to build some walkers that use passive dynamic motion in order to walk in a similar way. Part of our efforts in this project have been to recreate some of Tad McGeer's work in building mechanisms such as this one, and then to pursue some design ideas of our own, like this. This video will show clips of these two walkers and some others walking on downhill slopes, shallow ones, about 1 to 5% grade. And then it will show some information on the details of our progression of ideas, as well as some information on some construction techniques and some additional important things that we learned creating these walkers. All right, so to start this project, we decided that we wanted to start off with a simple idea first, something simple that we could build fairly easily. And we also decided that we'd figure out how our intuition was on it. So we decided to take the concept of a walking wheel, as we term it. Our walker would consist of 2 legs here that would have circular arcs for feet, and those circular arcs would extend out to complete a full circle, which would be centered right at the pivot point of the 2 legs. In this way, the walker would act very much like a wheel rolling down, because as it would walk this direction, each leg would swing into place and connect the next segment of the wheel. So we figured that's a pretty intuitive way to do it, and we thought we'd start out with that. So we went down to the hardware store, bought some wood screws, and some other cheap materials, and for about $5 we put together a simple model of this, and just to see how well it would work and to get a feel for the dynamics and how difficult or easy it would be to build these. And the following is a clip of what we accomplished in the day that we put it together. Currently, the only portion of that walker, as our first walker that remains, are these feet, since we've recycled a lot of the other bits of wood in future walkers. But the first thing you'll notice on that tape is that our actual design uses 4 legs and not 2. That is, that the legs are paired. There are 2 inner legs and 2 outer legs. And that's to keep it from falling over laterally, so we don't have to worry about that problem. The other thing you'll notice is that the walker actually steps on pads that are carefully spaced along the surface. And that is to keep this from happening. You'll notice that if you were to walk this on a flat surface, that since all the legs are the same length, that they scuff. And that's a particularly nasty problem that's difficult to solve, but one quick solution to it is to put pads down. And so we made these pads, which are just simple hard cardboard pads. And through trial and error, we spaced them out just right on the ramp so that the feet could walk alternately on these pads. You'll notice that now that it's stepping on there, it's got enough clearance to swing without scuffing at all. And by giving it a push, you can get it to go from one set of pads to the next, and it will just swing without scuffing. So that was a simple solution to the problem. Another thing that took us a little time to figure out was actually how you start these walkers. You'll notice in the tape that Mike was starting it off this way, or give it a swing. This is a difficult way to do this and have it be reproducible. So in some later trials, we found that it was actually easier just to give it a strike right at the axle. And that way, if you give it the strike with the right impulse, then you can give it a good set of initial conditions, just like that. So let's go back and look some more at some of this walking, and we'll talk a little bit more about some of the details of what's really going on here. In particular, notice how hard the heel hits. This hard heel strike seems to be one of the main reasons it fails. In this clip, we added some extra weights at the torso, those round steel pieces on the axle, to try to minimize the bouncing and improve the walker's reliability. This seems to smooth out the walking motion, but heel bounce is still a problem. The problem of heel bounce seemed to be causing all the difficulties with reproducibility of walking this walker down the plank that we created. And it was fairly clear we needed to do something about this abrupt transition at the back of the foot where it would strike the ground. So we thought about perhaps sanding this corner down and making it smoother, or making some sort of dual radius foot where this one would be a different radius so that the foot could come down more comfortably. But we decided that a better idea would be just to extend the feet, make them longer, so that we wouldn't have to worry about the heel striking there. So what we did is we just made the same kind of feet, the same radius of curvature. We just extended them a little further. And we expected that this would solve the problem that we had with the reproducibility, that it wouldn't bounce off the pads and veer left or right unpredictably. So we did that. We added these feet. We also made some changes because the first walker we built was very quickly put together, and we really didn't feel it was going to last. So we went out and bought some better materials. We got some nice poplar wood. We added some angle brackets up here at the top for some reinforcement, so it wouldn't shake apart, and we added some the same way to the inner legs. We made the feet adjustable by having holes drilled through them and having some bolts run through with a little bit of slip, so that we could adjust the feet and position them right. We figured perhaps that was causing some trouble. So we'd adjust it and then clamp them together with some rubber in between just to hold them snug. We also added some rubber onto the bottoms of the feet so that we wouldn't have to worry about slipping. Now we tried this, and this second walker, to our surprise, worked even worse than the first one. We had a terrible time trying to get it to work. We don't have any video of it, but it just wasn't working at all. And we were puzzled by this. It didn't seem to make any sense. We figured we'd had the solution all worked out. And we thought about it for quite a long time, and we came up with this explanation. It's very difficult to understand conceptually, but let me offer this potential way of explaining it. Since our design inherently uses two circular arcs for feet which complete full circles, you could imagine this walker as being essentially two wheels hinged together right at the same axle, same pivot point. So effectively, if you were to give something with such a design, two wheels hinged together, if you were to give this a push, it would merely roll down the plank. It would not walk. Our design requires that, for walking, that one leg, the stance leg, be rolling while the other leg is swinging. And that kinematically cannot happen with this design. The only reason that it would work would be because of our pad spacing. The pads would periodically, when it would roll off the edge of one pad, suddenly the ground would effectively drop away and the leg could swing through. So it was the spacing of the pads and the size of the pads that determined exactly how this would walk. And we could force it to walk with any step size that we chose according to the design of the pads on the ramp. And this was no good. We didn't want this to depend, we wanted this to be a dynamic walker and not be dependent on pads. So we decided, well, if we looked at this, supposing we make the radius tighter here, so that instead of having the two fit together like two wheels of equal radius, they would fit together with some displacement, so that you would actually conceivably get this to walk. So we knew we wanted to have a smaller radius foot, but we really didn't know what radius to use or what size. So we decided that we should go and do some computer simulation to optimize what we would like to use in our next design. This program here was written in ThinkC, and it allows you to vary the various geometrical parameters of the walker. Listed here are the mass of one of the legs, the length of the leg, the radius of curvature of the foot, the location of the center of mass, the inertia about the center of mass, and the slope that this walker will walk down. Then below that are the initial conditions of the walker, the stance angle, and the initial velocities of the two legs independently. And at the bottom we can vary the integrator size, which tells us how precisely we can simulate it. Now, after pushing return, this will now simulate the walker. At the bottom, you can see a graphic representation of the walker, and at the top are scrolling numbers showing the state of the walker after each step, after both legs are on the ground. That would be the stance angle and the velocities of the two legs. Using this simulation, we can vary the geometrical parameters of the walker and the initial conditions to figure out what combination of geometry and initial conditions will be most optimal in our walker design. This is our third walker, as we term it, but really the only difference between the third walker and the second walker is that the third walker has a different set of feet. All the rest of this is the same as before. So now, here's a clip, a few clips of some of the walking of this machine with the new feet. I'll try a little smaller. Start with that. Okay. Now you'll notice that on the tape, you'll see that it would stop at the same set of paths each time. It would take something like 4 or 5 steps, and it would stop each time. And we found this to be rather curious. So we looked at it more carefully, and just looking at it by eye, it looked like it was leaning forward a little bit. So on that last catch, it was leaning so far forward that it would scuff, even with foot clearance. So we didn't really understand why this was happening. We decided to go do some slow motion work. And we'll take a look at some slow motion right now, and we'll be able to show you what's really happening. Pay particular attention to the angle of the swing and stance legs as the swing leg passes through. Here you notice the outer legs are swinging by right now. It's leaning forward just a little bit. Strikes again. Swings through, it's leaning backward a little. Now in this pad, the inner legs are now vertical, and the outer legs don't pass through until now, and it's leaning way far forward, and that's the reason that the outer feet scuff on the ground. Okay, so it looked like the problem we were having was that there was an imbalance there somewhere. And we decided that we should go and make measurements of the properties of these legs independently. And so we did a simple pendulum swing test and measured the inertia of these legs independently. And found out just from measuring the frequency of the swing that the inner and the outer legs would swing at two different natural frequencies. And intuitively, this would make sense that you couldn't get something to walk if they both wanted to walk at different rates. So we knew we had to change that. And after measuring them and we calculated where we had to add some additional mass, found that we had to add about this much. We actually use bolts. Right now we have a solid piece. But if we added a bit of mass here to the inner legs, we can compensate for the inertia that results from there being an asymmetry up here at the top. So we have a large crossbar on the outer legs that was adding to the inertia of the outer legs. So by adding this, we came up with much more reproducible results. And you'll see in the following clips that we were able to successfully get the walker to walk all the way down the plank that we constructed. Couple more. Well, this seemed to be working quite well, and we were very happy with it at the time, but we still couldn't walk it outside. We couldn't walk it on any surface. We had to engineer the surface with these pads, and that was making things quite difficult. And every time we would have to change a slope, we'd have to change a pad spacing, and we didn't want to deal with that. So we decided that the next thing we should do is to figure out some way to avoid this problem of foot scuffing so that the thing would pick its own feet up and out of the way. So we thought about this. We went on a lot of brainstorming. We thought, well, initially we could do it with some active control system, which would lift the feet up at the right time, or using some sort of cam system or servo motors or something like that. We've outlined a bunch of potential ways to do it in our report. But we still wanted to stick to something that was passive. We didn't want to have any active control systems on this at all. We wanted it to be a completely mechanical solution. So we decided to brainstorm on some ideas to see what we could come up with. In the process of brainstorming, we came up with some fairly interesting ideas. One of them we put together with some simple cardboard. It's a very crude model, but it should work for this. The idea is to have some mechanical system here lift the feet. And if you look at this mechanism, it consists of 3 links with a sliding joint here. And if you follow the motion here, you'll notice at the bottom of this leg, when it gets to the center, it's lifted up with respect to this one. So as I push this through, we get to this point where now the pin at the top begins to slide. And then now when it gets to this point, the other leg is now lifted higher. So you can see as this turns around, it lifts one leg and then the other alternately. And we thought, wow, this could actually work. But it turns out that it really can't, mainly because it's not a dynamic system. Every motion that this makes is entirely defined by these joints here. This maximum step size is defined. You cannot let this thing swing by itself like two pendulums. So we didn't think that this would be appropriate because it defines the step too well. We want the step to be freely defined by the natural frequency of a pendulum. So we thought about some other ideas, and we looked at this toy that our professor has, and this is called the Connecticut Do Nothing Machine. It's printed in on the back. It's a very simple toy. I'd like to zoom in on it. It consists of two routed out tracks here and there with some sliders that follow it. And as you turn this around, you can see that the sliders follow those tracks and produce a very interesting motion at the end here where you hold it. In fact, it appears to be an ellipse that it follows. If you take a look at how it swings, it comes out very far at its major axis here and very short at its minor axis. And we thought, well, imagine this as a leg. If you had a leg swinging like this, it no longer swings on a circular arc. And if you imagine the other leg as standing on a circular arc, this one would swing a little bit shallow, so it would appear to lift the leg up. And we thought, that might be an interesting way. What if we designed something with tracks routed out in followers that would provide this lift alternately on each leg? So we looked into designing this, and using this idea, we came up with another idea. This here is the idea that we came up with. And it took quite a bit of time to conceptualize this. This is not a very simple thing to think of at first. But there are two components here in this picture, on this diagram. One of them is this large block, which has one leg attached to it. And it has this path that has been routed out of it, very much like the Do Nothing machine has. The other component is this leg here, which has a pin follower and a slider here attached to it. And as this leg, this can swing with the pin following one of these two tracks. When the pin follows the upper track here, it lifts this leg up, and that's why we term it the swing leg. When it comes to this point, it can swing down, and it becomes a stance leg because it pushes that leg down farther with respect to this leg. So we figured if we were able to create some sort of a valve here and here, that we would be able to tell it which path to go on. And if we coordinate that with the steps of the walker, we could get it to lift its feet alternately. So we worked a bit more on this design, on the idea of having two valves here. And we just played around with some models. And we came up with this idea, which is basically what we had before. This is just the routed track that the pin would follow. Imagine this as the pin. First, the leg would start here and would start swinging. And when it gets to this point, it starts to push down. So one leg is extending while allowing the other leg to swing. And when it comes to this point, it hits the flip valve, which will be held with some sort of spring in here somewhere, maybe a torsional spring. And it would push it up and out of the way. When it gets to here, the torsional spring will flip the valve back. And thus, when it comes back to swing with the other leg, this leg will now be lifted, and this will become the swing leg. And it will follow the upper track. And then when it gets to here, we'd have another flip valve in this location, so that we could tell it effectively through the design to follow only one loop here on the tracks. It would not go back through the wrong track. So taking this idea, this seemed to be pretty good. The one problem remaining was that it seemed to be a complication to have two valves here, because both of them would have to be consistent, and it seemed like a mechanical difficulty. And we thought, wouldn't it be nice if we would be able to design a single centerpiece that would tilt? and accomplish the same task of defining the path that the pin follower should go along. So what we did is we went over to our computer-aided design program and played around with this idea. We knew the track that we wanted it to follow. And we came up with the idea of having the central cam. Now, this thing looks a little bit silly, and it struck us when we made this that looks kind of like a face. So you'll see in some of when we mention what this term called smile in some of our programs, that's referring to this whole thing, and it looks like a smile. But the idea here is that we would have our pin follower grab something like this. We would have our pin follower slotted into here, and this would swing down, and it would follow what we call the wobbler. This centerpiece is called the wobbler. The rest of it is called the trap. It would swing through here, and when it gets to this point, the force will just push the wobbler to define the next segment of the track, and the pin would swing all the way up to here. And it would swing as far as was necessary, depending on the slope. This is all left free, so at some point in the swing, it will swing up and stop somewhere and start to fall back. Before it makes it all the way back, there'll be a torsional spring which will flip this wobbler back this way. So that as it's coming back, it now follows the upper path, providing the lift for this leg. And as it comes across, it will tilt the wobbler back and follow through. The spring will flip it, and it will follow back. And so in this way, with the spring attached, we could get, theoretically, our walker to lift its own feet through this mechanism by following the correct path at the correct time. So this may still be a little difficult to conceptualize. It's very difficult to come up with this shape. It took us an awful lot of work to get to. But the best thing to do right now is to actually show you what our final project is and what we've done. Well, now we can get rid of this one in our third walker. And let me show you what the fourth one looks like, as I said. Oh, you won't need these anymore. We can get rid of them. In our fourth walker, we shouldn't need them at all. Here it is. Originally we called this walker 4. It now has a name, and we call it Weeble. It's a name that we decided on after great effort. But it seems to be appropriate because it doesn't appear to fall down very often. Now, I'll just give you some quick dimensions on these things. This is designed to be very similar to the third walker. The radius of curvature here hasn't changed. We just made the feet a little bigger and have to do some modification. We'll explain this all in detail a little later. But the design here is essentially the design that we were talking about earlier. This is all made out of plexiglass here, all these components. And here's our wobbler. And here's our track. Now let me show you how this works again, since this is rather difficult. In this leg here, we have 2 pins that go all the way through. This pin sticks in the slot up here, and this pin follows the track out here and around the wobbler. And attached to these pins are some roller bearings on the other side, and we'll show you exactly how this whole thing is constructed very soon. But to show you how it works, this part of the wobbler here is flipped by a small spring in the back. And as this swings through, say we're on interlegs right now. You see, as it swings through, the pin now follows the lower part of the wobbler track. It's now rolling on the bottom part here, and it lifts. You can see that it actually lifts upward as it rolls along there. And then it swings through. You can see the wobbler just flipped, and now it comes through. It just leaves the wobbler track and is allowed to swing as far as it needs to on the step. Now, on the next step, it needs to swing forward. And you can pan over a little bit. Now, it's the exact reverse. It swing through. Now it's defined that this will follow the upper part of the wobbler. And so you see, as it follows that upper part, the outer legs now lift. The wobbler flips right there. It follows through. It leaves the wobbler flips back, and this leg can go through. Now, what we'll do here is we'll show you a quick clip of what this looks like as it's walking, and this will give you a better idea for just how easy it is for this thing to move. So life is starting slowly.
No, it's scuffed there.
Turns out that balancing the inertia for this walker is even more important than on the third walker, since we have all this complication in the middle. So we have these added masses here that are being carefully positioned after a day's worth of work. And we put them on, and we've run tests, and it runs very well down the ramp. And now we'll leave you with some clips of some ramp walking, and then we'll show you some outdoor walking. We've achieved success in this way. The right one hits first.
Yeah, I noticed that. Headlights side. This slope starts out about 1.5%. It looks like it probably starts to increase down a ways. Parking lot of the Statler, and way up at the top, and right around here it's about 3.5% slope, and we measured it down there and it increases a little bit to about 4.5 or 5. It scrapes now and then, it usually recovers.
Seems to want to go near this car.
Yeah, the slope's getting pretty rough down here. Just pushing it to the limits. Is he gonna make it? That's how you get away without paying traffic. Parking tickets. Here's your own quad. There's Upson, and there's Glen. This is that long thing. It heads all the way down to the sundial. We're gonna try it. Pretty nice slope, something around 3%. Though it increases a bit down the ways. In front of the biotech building now. Line is to our right.
Little rocks.
They tried so hard.
Yeah? Alright. This can be really casual. Mike and Heather are just gonna show us some things about the walker that the walker. Walker 4, which is Weeble. Just to give you an idea of maybe some things that would be nice to know that you should know that we're not going to be here to tell you. So.
Well, just seen some clips of this thing walking, and you might want to know why all these parts are there. We tried to explain the wildlife before, hopefully get some idea of that. But there are a lot of parts which we had to think about before we started to make. And to get a closer look at them, why don't we just take the two legs apart? This was a design feature, in fact that they come apart somewhat easily. The first thing you notice, there's a bunch of holes all over this thing. When we first built this inner part with the plexiglass and added the wooden legs, we made a few tests of how the motion would actually work. And this whole set of inner legs was really heavy, and it was really restricting the motion a lot. So we put the thing on a diet, trimmed off some of these extra pieces, put a few holes in here. This honeycomb pattern was designed to reduce some of the weight without compromising too much of the strength. We also did the same thing to the feet. Drill holes in through here in a similar honeycomb pattern, and the feet are still pretty strong.
Plus, it looked kind of interesting.
Yeah, it looks really cool. Makes it look high tech, like they actually had some purpose. So the other thing, if we look at the outer legs, are these added masses right here. Obviously, the inner legs and the outer legs are dramatically different, but by adding these extra masses on here, and by adding these extra masses on, we can effectively make these two, the inner legs and the outer legs, dynamically equivalent. And we do that by adding the correct amount of mass and adding it in just the right location so that the center of mass and the inertia of these two components are exactly equal. To do some of these testings to figure out what the inertia is in the center of mass, we determine the center of mass by taking this thing, putting it on its side, and basically balancing it across a beam until it balances sort of nicely. That's how you determine center of mass. Inertia, we determine the inertia by, at least for the outer legs, we remove these pins right here, which left a hole there, which we could insert a shaft through, and basically set the thing into a pendulum swing, letting it swing about that shaft.
Take a look at the pins.
Oh yeah. Well,
These ones.
so that's how we can test the inertia of the outer legs. Once you know the frequency or the period of the motion, you do some calculations to figure out what the inertia is about its center of mass. For the inner legs, to do a similar pendulum test about the inner legs, what you do is you remove the wobbler in here, and you replace this wobbler shaft with just a long 1/4 inch shaft, and you can do the exact same pendulum test that you did with the outer legs as with the inner legs as you did with the outer legs. So you can compare the frequencies, compare the periods of motion, and basically make these two legs dynamically similar, even though they look a lot different.
You'll also notice these two so-called antennas on the back of the feet, which were added also to balance the inertia, slight displaced mass, which helps.
The actual explanation for these is somewhat shady, other than the fact that we sort of looked at it and it seemed to be something wrong, so we just tried adding things until it worked. This walker in general is a little bit more sensitive than walker number 3 was, just because there's a lot of components here, and there's a lot of little adjustable things and things you can balance. So to get this to work, it is a bit of a lot of little tinkering and playing. Even now, there's still some stuff that could be done to get this to walk better, just by screwing things in and out and adjusting them. So actually, that's a good time to talk about things that we can adjust. If we look at the inner legs, we have the two plexiglass smile tracks, which we call smile tracks. They're connected by aluminum shafts. These shafts actually used to be steel, but as part of that weight reduction, we had to switch to aluminum shafts. And we machined the shafts ourselves. It used to be a solid, smooth shaft, and we put threads on the end. So each one of these nuts, or each one of these shafts, can be loosened, and the nuts can be slid along to effectively pull these tracks in or out. And since you have 4 of these, you have a lot of flexibility in how you can adjust these. And there's 2 purposes really to leaving all that flexibility in here. One of them is to keep these tracks perfectly parallel, or at least pretty close to parallel. The other idea is to keep this wobbler snugly fit. In other words, this wobbler, if the length of this wobbler connecting between the two plates it's not adjustable. It's a fixed shaft in there. So what we did is made the distance between the 2 plates adjustable, so that we could push them in or out, so that the wobbler fits in there nice and snugly and doesn't have any extra movement in or out. In other words, it can't wobble in or out. Only wobble sideways. What's the other adjustment? Oh, okay. The pins on the outer legs. Outer legs. These pins, first of all, talk about how we made these pins. These pins also originally used to be aluminum, and we went to steel, actually adding weight, but it wasn't much weight. We started with aluminum. We initially tried to make these out of steel. We tried starting with a smooth steel shaft and machining threads onto the shaft, so we had this threaded adjustability. And that was difficult to do, mainly because steel is pretty hard to machine. Trying to cut steel threads using a steel bit. There's sort of
Steel's no fun to work with. We
Yeah.
recommend not using it if you can avoid it.
Steel's really hard. So after concluding steel was really a pain to work with, we switched to aluminum. And we took a bare aluminum shaft, tried to put threads on it, similar to this. And that was okay. It wasn't too hard to put the threads on, but unfortunately these pins take a lot of abuse. They're banging around inside the track, and there's a pretty strong moment about here. And in order to keep them from wiggling around too much, we have to clamp these steel nuts on pretty hard. When you take a steel nut and you clamp it very tightly onto an aluminum shaft, that doesn't work either. And pretty soon we were just stripping my threads off the aluminum. So this time we went back to steel. We went back to steel. We went back to steel, but instead, last time we tried taking a bare steel shaft and putting threads on it. This time, the exact opposite. We took a threaded steel shaft, which you can buy all over the place, and basically removed the threads on this one end so that the bearing, we have some place to put the bearing on. These have worked out great, because you can clamp them down pretty much as tight as you want, and it moves in. Zoom in on one of the pins.
Yeah.
Each pin has a portion here, which is machined down to remove the thread, and then a smaller portion, which is 1/4 inch in diameter, on which we insert a bearing. The bearing's the part that rolls around on the track.
See if I can get it a little closer.
These bearings are held on. These bearings really should not take any lateral force. So initially we just tried sitting them on there, but they did wiggle off a little bit. So we wanted to be able to still pull them off in case we changed our mind or something broke. So they're just barely held on. We took a tiny little dab of rubber cement, and sort of squished it on there, squished the bearing on there, and it's been enough to hold it. But if we need to pull it off, we can just yank it off without damaging it. each of these pins is adjustable in the same way that the smile track is adjustable. You can loosen these screws and effectively move the pin in or out. And the reason for that is, if we zoom out,
Gotcha.
the reason for that is when we try to assemble this thing, zoom in on the top.
Right there.
Okay.
You hold this forward.
Can you remember? Yeah, just, okay. We assemble this, these two legs. We're dropping these pins into the smile track. And they must fit in there snugly so that it prevents the motion of going in and out. The ends of these pins are rounded so that when it's pushing in or out along this track, it slides along pretty smoothly. Plus we add some silicone lubricant to the track so that the ends of these don't dig in too much and they can slide along. And the other reason they're adjustable is so that, hang on. These two pins are pushing along lower parts of the track. These are pushing along the upper part of the track. In order to keep these legs straight and lined up, you need to adjust these things so that while the upper pin, while the lower pins, I'm trying to explain.
It's just a lateral, like a camber in the legs or whatever. You can adjust all those 4 pins independently. You can adjust the lateral tilt of the legs just so they're upright when they're sitting
Yeah,
inside.
for instance, we could push this pin out a little further and pull this one back. You could still keep all the things touching the track, but it would be, of course, angled the wrong way. So by pulling these in and out, you get it angled just right, so that everything's lined up pretty smoothly.
Okay.
Next part. Oh, smile track.
The track.
How did we build this? Right.
This is the complication.
We sort of explained why we designed this as we did. We'll probably do a much better job of it in the report. This whole track had to be NC machined. The pattern on here, the shape of it, is pretty complicated, especially the shape of the wobbler. Too complicated to cut by hand. Plus, we needed 2 tracks exactly the same, and the only way we could figure out how to do that was to NC machine it.
On the NC code in the report.
Yeah, the NC code is back there. In order to give the wobbler something to stop against, try to see if it's clear.
Get a little closer.
In order to give the wobbler something to hit up against so it can only go so far, we also machine these things we call the stops, which are basically just pieces of a circular arc, whose face right along here matches up exactly with the face of the wobbler, so we get a nice solid contact. Originally we thought of just using a couple pins along here, so we'd glue some pieces of plastic on there so that the wobbler could only wiggle so far. Wiggling wobbler.
Terminology hasn't all been totally worked out yet.
But this small plexiglass piece has to support a lot of weight, and we figured if we used a slightly more accurately machined piece, that would give us a nice surface contact along here, rather than just a pin, which is going to give you a point contact. The surface contact would reduce stresses a lot and make this thing a lot more reliable.
It's just machined to fit exactly to the shape of the wobbler. Those are super glued in.
Yeah, they're attached to be super glue, so you're never going to get them out. You want to build another one. But
You have to build another
You
one
gotta
if
build
you want
another
to
one,
change
yeah.
anything.
I guess I can attach this to show how the wobbler's attached.
Yeah.
I don't know, take it apart. The
That's
wobbler.
There's a piece of plexiglass, you point to that. There's one on the surface of the wobbler.
This is as close as I can get to it.
The real thin,
Glass washer.
yeah, a real thin piece of plexiglass glued to the top of the wobbler Basically, that acts as a washer. The wobbler has a 1/4-inch hole in it, which slides onto a 1/4-inch shaft. But this little plexiglass washer has a much smaller hole in it, just exactly the size of the screw threads, so that we can insert the wobbler on top of the shaft, and this plexiglass washer holds it snugly up against there. And then we just tighten the screw on top, which holds it in place and plus prevents it from twisting too much.
You know, the one thing we can't see in the video is that that wobbler is not touching the back face of the track. It's actually, can you show it? It's spaced out, but with
You can see through the plexiglass. You see this white piece back here. What that is, it's a piece of nylon. It's a nylon disc with a sort of a little nipple that sticks out. Little nipple part pushes up, or comes through this smile track, and the back of this wobbler rests against that.
you might be able to bring it up really close on the camera.
Oh, that'll see through it. It's all clear
Alright,
too, so
yeah.
it's,
No,
you can't tell.
Yeah, I can just catch it there.
And the purpose of this, this fulfills two purposes. One is that this white disc has a hole in it, in which this aluminum shaft comes out. So nylon and aluminum is pretty smooth. And
smooth enough.
the other purpose is that little nipple that comes pushing through the smile track. The wobbler rests right against that nipple, and it raises it, keeping it from scraping against the back of this track as it wiggles. As the wobbler wiggles. And,
Well, wobbler's only touching the nylon.
the spring mechanism on this thing.
All right, where is it? That's it.
Both wobblers wiggle together.
Wiggle, wobble.
You can actually see it.
You get the idea.
Because they're connected by that shaft. And so we really only need one spring to return it. The spring is just a cotter pin, a hole through the shaft, and then just a little piece of spring steel attached to it. So one spring keeps them both together. And the reason we wanted them both turning together is just to try and coordinate the motion, just in case this thing gets a little bent and out of whack. They at least try and move together. What else? Oh. Okay. Let's take a look at the feet. Feet, explained earlier, have lots of holes in it and angles and stuff. That was all for weight reduction. But the other feature of this thing is an adjustability feature, which is giving us all kinds of headaches. The feet are attached on with bolts, and the holes in the legs are about the same size as the diameter of the bolts, but the holes in the feet are slightly bigger. This allows us to put the feet on and wiggle them around a little bit until everything's lined up. Then we can clamp the bolt down really tightly. A little piece of rubber in between
If you could tell that little piece in the back, the inside.
Yeah, there's a back. Nuts with real big washers on each side, so we don't press into the wood too hard. We thought this would be a great idea. Someone would be able to adjust the feet, get everything lined up really well, just in case we made some mistakes in constructing the thing. But unfortunately, it doesn't work as well as we had hoped. One thing, it's pretty hard to figure out how to adjust these things to get everything so this circle lies exactly as we had planned. In other words, the center radius of the circle lies somewhere. It's perfectly centered along this thing. If we tilted it, say like this, then the center would lie somewhere over here. Unfortunately, we have no good way of checking where the center of this thing lies. And really just have to play around until we think we get it right.
That's one of the things we mentioned in the report is somebody can come up with a better way to adjust those feet and still hold them on.
Oh, and the other problem they can also move in and out because the holes are pretty big. So there's a problem of adjusting the length exactly correctly. And if the feet are misaligned, it definitely causes problems, because you can imagine if we take this foot, misalign it, we're pulling the center of it somewhere over here. effectively we're totally screwing up the dynamics that we spent all that time in computer simulation studying. We're pulling the center of mass away from where it used to be, and things get messed up. So
The walker starts to turn instead of walking straight.
Mhm.
Things like
yeah, if one foot hits earlier than the other, and things starts to turn. Actually, that's another thing. Could be cool to work on. You can see it in some of our outdoor video. Sometimes when this thing hits, one foot hits a little earlier than the other because they're misaligned, which causes it to turn, and it does weird things. That could be a possibility for adding some kind of steering control to this thing, just purposely misaligning the feet so that it spins as if because one foot hits a little earlier than the other. Although it would be a pretty complicated thing to do. So I don't know. One of our mistakes could end up being a really cool idea. What else? Foot clearance. Let me reassemble this thing. Weeble walks pretty well outside. I think our record is 47 steps.
47. Great. I think it should be on this tape. Maybe we'll put it on. We haven't decided yet.
But the record, you pan down.
Yeah. Down.
No,
Okay. There we go.
the wobbler gives us pretty nice clearance while we designed it for a half-inch clearance. You can see while the two legs are passing perfectly or exactly right by each other, we have almost exactly half-inch clearance. But as this leg swings through, that clearance drops off. And then it starts to increase again as it passes by the wobbler. Why did this happen? Well, it's because we sort of screwed up.
Well, we didn't exactly screw up. We just didn't think of it.
We just didn't design. We designed for a half-inch clearance through here. And then the half-inch clearance slowly dies off at some point until it gets back to just the regular motion. Well, our die-off period, in other words,
a little too short.
It comes down too quickly as it
comes
passes
down
from here to
exactly.
here.
Comes down too quickly, and you notice how critical it gets right there. That's not a lot of clearance.
In the videotape.
So the wobbler could be redesigned so that it still had a half-inch clearance right at the center. That seems to be fine. But make it maybe a little wider throughout the entire swing to give it half-inch or maybe a little more clearance through here. And probably prevent a lot of the problems that we encountered on the videotape.
On our design, specially designed slope, perfect slope in the lab, it seems to work pretty well. But once you take it outside and get some varying slopes and just continuities in the pavement and stuff, it starts to scuff because the clearance isn't quite as good.
Ideally, when we're at the vertical, go down.
Go down.
When we're at the vertical, we get this half-inch clearance, and then it starts to drop off. But then it comes back up again as it starts to swing through. What we can imagine would be perfectly ideal is if that half-inch clearance, you design the wobbler so that the half-inch clearance was almost continuous throughout the whole swing. So, I don't know, that
Should I
involves-
take a look at the wobbler?
Yeah.
What has to be changed here to do this?
Oh, you can't see it, but
It's kind of hard to see. We're just thinking about thickening that part.
center of
So,
the wobbler gives you a half-inch clearance, but as you keep going, that half-inch clearance drops off. And what we envision, a redesign of the wobbler would make it a little wider,
Yeah. So that maybe this portion over here is a little bit wider than it is now and lifted.
right towards the ends.
That's one of the biggest problems. Well, the two biggest problems with this walker are that the wobbler needs to be redesigned and that the feet are pretty hard to adjust, making all this mass balancing kind of tricky. For the reason we had to stick those antennae on the back just for the hell of it, really, to get it to work.
Is that all we have?
I don't know how to prevent this other than making it out of a stronger material. This thing kind of, it's a little flimsy because you made it out of wood.
Yeah, wood is cheap, but it has this problem. It warps and it bends all over the place. So it's not as stable as we'd like it to be.
So it can wiggle like this. We added this metal crossbar across it, trying to prevent that for the inner legs, and it does a pretty good job there. There's really nothing you can do about the outer legs, because they have to be able to swing through freely, so the only place you can connect them is way up top.
Top. There we go.
Top.
Just top.
So this crossbar up here has to support this whole entire line.
All right.
And wood just isn't all that great for doing that. This could be redesigned out of aluminum. I think we could probably do it without getting anything too heavy. And that wobbling does cause some problem. You see, when it's walking, it does vibrate a lot. And for a while, it was actually tending to vibrate some of the bolts off. So we fixed that by using steel. And some of those vibrations, they just don't look good.
Well, I guess that's all. All this stuff is outlined in the paper, and part 3 on future ideas. So we haven't described everything, but there are a bunch of things that could still be done on this project. So, yes, that's all we have for suggestions for you. Thanks for watching us. And
Come back again.
maybe we'll see you sometime when we come back for homecoming or something.
Yeah, this better be walking uphill by homecoming.
We do want uphill motion. Adding power was something we wanted to do in the beginning, but just never had.
Sidetracked
At a
on
time.
Fitzgibbon.
Yeah, Fitzgibbon takes a lot of thought.
We're pretty happy with this concept of the passive passive
Passive
avoidance. The
scuff
PS
avoidance,
Our
PSA.
PSA system,
Yeah.
passive scuff avoidance system.
You don't believe how difficult it is to come up with some simple acronym for something.
We're pretty happy with the fact that we've now decoupled the problem of foot scuffing with what, to us at least, seems like the logical next step is to add power. We originally thought of adding more complicated, some kind of cam thing at the foot, which could solve both foot scuffing and power, and add power at the same time. But things started getting complicated because you're trying to do 2 things at once using one cam and other things wiggling around. So now the problems are decoupled. Foot scuffing is solved. You can add power in a bunch of different ways without trying to worrying about what's going on.
What a casual look. We should probably introduce ourselves right at the very end of the tape.
Oh, yeah.
I'm Glenn Kenslow.
This is your host.
I'm host at the beginning of the tape.
I'm Mike Bray, and this is Heather Latanzio. We're the masterminds behind this.
We've been working on this past semester, which is the spring of '92.
And this is senior week right now.
Yeah. Well, I hope this is useful.
Yeah, because this is senior week. Spending time.
Yeah.
We should
Yeah.
also mention that we worked with Chris Pasher Coachling on this project, as well as Andrew Ruin and Mike Coleman.
They've given us some useful suggestions in our regular weekly meetings.
Andy and Mike are both from Theoretic and Applied Mechanics, and they've been helping, giving us lots of ideas. And Mike is currently working on something similar. He's into simulation studies, study of just passive things in general. He's doing some really neat stuff. Probably want to go over and talk to him.
We'll be doing that for a while.
Yeah.
One other thing, if you ever want to do NC machining on these, we suggest to figure out how to do it yourself, because it's difficult to get the scheduled time in on the Bridgeport around Jeff and Wes in the machine shop. So it would be to your advantage to learn how to do it yourself. And
That's
save
not
yourself some time.
Not just learning how to write the code, we're talking about
Yeah,
learning.
we're actually putting it in the Bridgeport, setting it up, and running it.
Go. Yeah, these took a lot longer to build than we thought, mainly because we spent a lot of time. A lot of time.
A lot of time.
A lot of time trying to get time
Yeah.
on the machine and worrying
Yeah,
about checking points.
you'll find out.
Any other things on here?
I think we're all set.
That's about it.
That'll do it. So long.